All right, guys. So how do we deal with reversibility? So that's our task for this next section. So if we go back to thinking again about protein folding, right? And we think about that as, in this case, a reversible process. So again, we have that forward rate constant for folding, that reverse rate constant for unfolding, right? How do we describe this process kinetically, assuming we're explicitly not at equilibrium, assuming we had, say, 100% of the unfolded state, triggered folding? Why does this process proceed kinetically the way I showed you last time? Specifically, it appears to go faster than a simple unimolecular process, and the amplitude of the change is smaller. All right, okay. Well, the first thing we've got to do is write out the rate equation for this process. So if you remember when we talked about reversibility in the context of equilibrium before, it's not so hard, right? We've got two pipes. We've got a pipe going out and a pipe coming in, if you think about my water tank analogy. So we would write that as something that looked like this. So minus change in the concentration of U with respect to time, right? Well, that's the kind of how much it's going, the rate at which it's going to disappear. But we've got this input, Kf, right? Or sorry, it's output, Kf, times concentration of U. That's going out of the tank. But we got this coming back in. So Ku times concentration of the native state. That would be the unfolding rate. So let's make this a little bit simpler, right? And make that, let's just move that sign over, because that'll make things a little bit easier. So we'll move that sign from the left side over. So this is now minus Kf, concentration of U, plus Ku, whoops, let's make sure that's a good lowercase, Ku, concentration of N. Okay, so that's great. We've got now another simple ordinary differential equation we need to solve, but we've got two variables, right? Boy, if you don't want to have to deal with, partial differential equations and all that kind of stuff, it'd be really great if we could make that go away, have this turn into an equation in one variable. And it turns out there's a piece of information we know that lets us do that. Specifically, we know something about the total amount of protein in the system, right? We know that the concentration that we start with, remember, we're starting this reaction from, fully unfolded state is the way we're sort of thinking about it, right? Well, we know that what has to be true is that that's the total amount of protein we put in, which means at any given time, the amount of unfolded protein plus the amount of the native protein must equal the amount we put in to begin with, so U sub 0, which means concentration of N at any given time has got to simply be equal to the amount we started with, the total amount of protein we started with, U sub 0, minus concentration of U at any given time. Well, that's cool, because I can use that idea and I can substitute that in here to get an expression that's now all in a single variable, right? Which would be du dt is equal to minus Kf, concentration of U, right, plus plus Ku times concentration we started with minus the concentration of U at any given time, right? Well, that's cool. That's not so bad. So now multiply through and group some terms. We end up with an expression that looks like this. We can say, oh, so that now has got to just be equal to minus Kf, concentration of U, plus Ku, U0, minus Ku, right, concentration of U. Okay, group some of these terms up, and we now end up with our differential equation in a single variable, single dependent variable, that looks like this, right? That's cool. That means this has got to equal minus concentration of U times Kf plus Ku, right? plus Ku concentration of U0, right? Pretty easy, not so bad. All right, so we can now sort of begin to group our terms a little bit here. So we can say, well, differential equation, so let's put all the terms with respect to our dependent variable here, U, over on one side, concentration of U times Kf plus Ku, and that's just got to equal Ku times the amount of protein we started with. Cool. All right. Now, as you would do when you get to this point, you have to solve. There's our differential equation. That's what we need to solve. We could proceed the way that I showed you guys last time, separating variables, and then sort of grind through that. But it turns out, in this case, there's an easier way, right? And this would require you to either remember some of your basic calculus or ODEs, and sort of have an instinct for how something like this can be solved. Look at that and recognize that that really is the derivative of a simple, another simple function. Or you would need to have access to like a symbolic math solving tool like Mathematica or something. But in either case, the easy way to solve this differential equation is basically to multiply through with this term, e to the kf plus ku t, right? So if we multiply all the terms in that equation by that term, we end up with something that looks like this, which is that, whoops, wrong color. D, derivative of u with respect to time, times e to the kf plus ku, ku-t, plus concentration of u, come on, tighten that up, times kf plus ku, e to the kf plus ku-t, and it's simply got to equal ku, concentration of u0, e to the kf plus ku-t. I got sloppy here. Okay, right? And you're like, oh, man, that's looking ugly and evil and stuff. But if you look at, in particular, this sort of the left side of this equation here, right? Look at just this side. That, if you remember some of your basic calculus, that ought to look familiar to you, because that's basically the consequence of applying a derivative, well, applying product rule and chain rule to a relatively simple function, which is the following. That, like I said, this side is equivalent to the following, which is this, that is the derivative with respect to time of the following product of two functions, u and e to the kf plus ku t. Well, that's cool, right? And then we can just set that equal to the right side over here, which is now just ku, amount of protein we started with, right? E to the kf plus ku t. That's cool. Now all we have to do is solve that, right? Which again, we're solving a differential equation here. Generally, that's going to involve integration. Well, integrating that sucker is not so bad, right? Especially over here on the left side, because now all we got to do is run that integral d dt u e kf plus ku t. It's now going to equal integral over here ku u 0 e to the kf plus ku t. Well, solution to that on the left side is trivial, right? The integral and the first derivative just cancel out, so that's easy, which means that u multiplied by e to the kf plus kut has simply got to equal, ku is a constant, starting concentration of protein is a constant, so those move outside the integral. That's easy, right? So now all we have to do is integrate that exponential. Turns out that's not so hard either, right? You just end up with the same function or the same form here, t, but we have to divide our pre-exponential term here by what's multiplying our independent variable there, which is essentially kf plus ku, right? Cool, except for one more thing. We have a constant of integration here, right? That's not trivial in this case. Bummer. So we still don't really have a function of u with respect to time until we determine that constant of integration. All right, this is one of the names of the game in solving differential equations in a lot of cases, is now applying a set of boundary conditions, right? So that's our basic beginning of our solution. We've got to do something with that constant of integration, and you solve that by setting some boundary conditions and solving then for C. And in this case, our bounding conditions are really trivial, which is basically at t equals 0, we know the concentration of the unfolded state at function of time at t equals 0. That's just going to equal the concentration of unfolded state we started with, right? That's easy. All right, so let's apply that. So now we go over here like, okay, we've got u as a function of time, e to the kf plus ku t equals ku divided by kf plus ku, u at times 0, e to the kf plus ku t. But we're going to say when t equals 0, what happens to this term, right? When t equals 0, that whole exponential term, right, goes to 1. Same here, right? Oh, that's kind of convenient because now we can rewrite that as simply concentration of u at time 0 has to simply equal ku divided by kf plus ku, concentration of u at time 0, right? Right? Oh, I dropped a term. Sorry, over here. We have to have our constant because that's the whole point. All right, so there's our constant. Well, now that's easy because now we can solve for C, right? Which is trivial. C has just got to be equal to concentration of protein we started with times 1 minus Ku over, oops. Kf plus Ku, right? Cool. Right, so now that's what we needed. Now all we've got to do, right, is take that expression here, substitute that in for our missing constant C there, and we're off to the races. All right, so let's see what that looks like. All right, so I'm just going to write that out again so it's clear. All right, so we've got concentration of U at time t. Remember, that's what we're after. E to the Ku plus Kf t is going to simply be equal to Ku divided by Kf plus Ku, concentration of U at time 0, E to the Kf plus Ku t plus C. All right, now before I substitute in for that constant, which we just derived there, I want to rearrange this a little bit, because remember what we're after really is a function of that describes the concentration of U at any arbitrary time, right? That's what we want. So let's go ahead and divide this whole thing by that exponential term. Right? It's going to make life a little bit easier. So now that'll give us Ku over Kf plus Ku times concentration of U at time 0, E to the Kf plus Ku t divided by E oh, come on. E to the Kf plus Ku t, right? Plus C e to the minus Kf plus Ku t, right? So now, here we go. There's where we now bring in our substitution, right? Substitute that baby right in there. And now we can rewrite this thing, but we can do something else in the meantime. See this term here? Right? That's basically, yeah, we can make that go away. That's 1, right? So we can rewrite this whole expression, canceling that term out, as concentration of U with respect to time is just equal to Ku over Kf plus Ku, concentration of U time, plus now concentration of U at time 0 times 1 minus Ku over Kf plus Ku e to the minus Kf plus Ku t, right? So all we did, right, was you'll recognize from our application of the initial conditions, there's our constant integration. All I did was substitute that in right here, same term, it's right there. All right, well, let's see if we can simplify this thing a little bit. We can simplify this for sure, because we can recognize that that's just Kf plus Ku over Kf plus Ku minus Ku over Kf plus Ku, which is just going to be equal to Kf over Kf plus Ku, right? All right, so that'll simplify things a little bit. It won't be quite that ugly, right? So let me just write that out again. Now, our function of U as a function of time is simply equal to concentration of U at time 0, Ku over Kf plus Ku, right? Plus concentration of U at time 0 times Kf over Kf plus Ku, right? times e to the minus kf plus ku t, all right? Okay, well, we can simplify that. Let's yank some terms out of that sucker. That would be equivalent to saying, well, concentration of U at time 0 divided by Kf plus Ku, right, times Kf e to the minus Kf plus Ku T plus Ku, right? And we're done, right? That is the derivation of the unimolecular reversible rate law. Okay. Whew. Wipe your brow, right? Sit back. Okay. Great, glad that's over. Okay, but fine. But look at that expression for a second. And specifically, look at it with respect to what the unimolecular irreversible equation would look like, right? Remember, that was simply this. Right? So if you look at the form, the basic form of that equation for a second, you'll notice some really close, or hopefully, some really close parallels mathematically, right? You kind of have a situation here, right, with a basic form of this equation where you've got this sort of stuff out here that multiplies an exponential term, sort of, you know, this pre-exponential stuff, right? Then you have this exponential term right here, right? And then, okay, we've got a little extra over here. We've got this sort of like, you know, addition sort of baseline component. But if you look at this in basic form, right, we got pre-exponential stuff and then an exponential term. So the thing that should immediately jump out at you, if you think about that, you're just looking at that, right, is look at what's in the exponential that's multiplying our independent variable here, right? That's essentially a rate constant. In this case, it was simply the forward rate constant. But now you can, another way to write this is you could say this is like a K observed rate constant, which is, I think, how I showed it to you guys when I did that plot. But that K observed is no longer a single rate constant. It's now a sum of two rate constants. Specifically, it's the sum of the forward and the reverse rate constant. So if you remember, what governs the halftime, right, of an exponential decay is that rate constant. All right, it's the constant that multiplies that independent variable, tells you how fast the decay is going to go. You can now see that in this case, the reason the K observed for that reversible process is faster is because the rate constant is larger, because it's the sum of the forward and the reverse rate constant. And it's a consequence, again, of the simple mathematical description of that reversible process and its solution, right? Another way to sort of intuitively think about that is that because the process is reversible, in principle, it doesn't have as far to go, so it can get there faster, right? That's, some people find that a helpful way to think about this. Okay, but it's all, we've also got that smaller amplitude term, right? So the reversible process we did, right? If you remember, it doesn't come down here as far, right? So where is that coming from? All right, so a relatively easy way to illustrate that is to think about, well, out here, let's say, you know, at infinite time or whatever, right? Over here, t is approaching infinity. This thing is going to hit something, or it's going to reach a point that we've talked about before. It's going to reach equilibrium, right? So we can think about what this expression would look like when t approaches infinity, or essentially the system approaches equilibrium. Let's see what that looks like. All right, so at that point, we can just write that out. Let's say concentration of U as t approaches infinity. That's just going to be equal to concentration of U at equilibrium, right? Okay, so that's just going to be equal to concentration of U. If we just write out that equation, the rate law again, divided by Kf plus Ku, right? All I'm doing is just writing this back out again, times Kf e to the minus Kf plus Ku t plus Ku, right? All right, but if this goes to infinity, right? That gets really, 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 really big. What happens to that quantity? Remember, you're multiplying by a minus here. So when the independent variable gets really big in an exponential like this with a negative sign, this goes to zero. That term goes to zero. Right? That lets us write this out a slightly different way, right? That means is that this equation now would simply be equal to concentration of U times 0 divided by Kf plus Ku, right? Times Kf times 0 plus Ku, or the concentration of U at equilibrium would simply be equal to concentration of U at time 0 times Ku over Kf plus Ku. That's equivalent to the endpoint, like I said before, where the reaction hits its equilibrium point. And because you don't get to the point where you use all the U completely up, right? The observed amplitude is smaller because you're multiplying the total amount you start with times this additional term. It's basically unfolding rate constant divided by the sum of the forward and reverse rate constants. And that sets that equilibrium point. And you're like, okay, fine, right? Seems a little fishy, kind of you did it that way. You kind of backed into equilibrium by just assuming time goes to infinity, right? So really, is that really the right answer? Well, let's do it a different way. We can think about this another way. Remember the equilibrium constant, right? The equilibrium constant, again, is just the concentration, the way we've done it here, of product native state divided by the unfolded state, which we know has to be equal to, at equilibrium, has to be equal to, if you recall our discussion about reversible processes at equilibrium, just the ratio of the forward rate constant, folding rate constant, divided by the reverse of the unfolding rate constant. Okay. What do we do with that? Well, remember that trick we used at the beginning of this little excursion to get rid of the extra variable. We know the total amount of protein between the unfolded and the folded states has got to be equal to the total amount of protein we started with, which means I can write this out a slightly different way. I can say, that means Kf divided by Ku has simply got to be, because I'm going to rewrite what I have up there again so you can just see. That also has to be equal to then concentration of U divided by, that I start with, divided by concentration of U at equilibrium, divided by the concentration of U at equilibrium, right? Oh, jeez, one of those days. Right? That's cool. I can rearrange some terms and just solve that baby, right? And say, well, okay, that means concentration of U, or sorry, Ku times concentration of U I start with minus Ku times concentration of U at equilibrium has got to just be equal to Kf times concentration of U at equilibrium. Okay, keep solving that, grouping some terms. That means Ku, concentration of U at time 0, is just going to be equal to Kf, concentration of U at equilibrium, right? Plus Ku, concentration of U at equilibrium, right? I can group a little here, concentration of U at equilibrium times Kf plus Ku, right? So if I solve that for the concentration of U at equilibrium, what has to be true is that the concentration of U at equilibrium is just equal to Ku divided by Kf plus Ku times the concentration of U I started with. And if you compare that to that, they're the same. Okay, I wrote it out a little bit differently. All right, I put the U on the other side. Here, let me rearrange it so that it looks exactly the same. That may be a little nicer, right? Concentration of U, 0 times, excuse me, Ku over Kf plus Ku. Okay, now they look the same. Right? So the assumption of time going to infinity got us with the basic rate law, got us to exactly the same place as just starting with an expression we know has to be equivalent to equilibrium, which means the explanation for why these reversible expressions, rate expressions, do not show faster kinetics and a smaller amplitude compared to the same process or the unimolecular process, right? So this is the unimolecular, and then this would be the reversible, right? Okay. So again, this is a type of process, this reversible unimolecular process, that's really quite common, and it's important to understand why it doesn't behave exactly the same way as an irreversible process, and that to really keep in your mind that the rate constant for a process like that is going to be the sum of the forward and the reverse rate constants, right? Okay.